Okay, before we go over the proof for area of a square, we find it appropriate to go over some axioms first. We have axiom 1, which states that the area of a square with 1 unit side is 1 square unit. We also have axiom 2, which states that if you let A, B, and C be magnitudes such that A is a ratio to B is equal to B is a ratio to C, then A has the duplicate ratio of AB. That is, AC is a duplicate ratio of AB. We can also go over some definitions of ratio and magnitude. The Euclidean definition of a ratio is basically any sort of relation in respect of size between two magnitudes of the same kind. And magnitude, brief definition, is a measure of how big something is. And from this definition we can continue proving the duplicate ratio, and we reach the conclusion down here that the ratio of A to C is equivalent to the ratio of A to B squared. And we can use this for our proof of area of a square. So I'm going to turn this over. So we let two squares, ABCD and square EFGH. The side unit for the EFGH is 1, and for ABCD is, we can call it L. By axiom 1, the area of EFGH is 1. By definition, we can claim there's a ratio between these two squares such that L is a relation to 1. By definition of duplicate ratio, ABCD is equivalent to EFG, which is equal to this right here. That is, the ratio of this is equal to this, which is equal to L squared, which we can break down to L times L. So the area of the square ABCD is L squared, which, like I said before, is L times L. And since the definition of a square states that all sides of a square have to be equal to each other, we can generalize that for all squares the area is length times height, which is just L squared.